Okay, thanks. So we'll start the second part of the morning session with a talk by Lorenz Eberhardt, and he's going to evaluate one-loop string amplitudes.
Right. Thanks a lot to the organizers. Thanks for organizing this very nice conference and inviting me to give a talk. And indeed, I want to talk about some recent progress that we made in actually getting numbers, similar in spirit to the previous talks from string theory, and actually evaluating one-loop string amplitudes. And this talk is based on a collaboration with many fantastic people. So my student Marco Baccianti, Jivan Chandra and Tom Hartman at Cornell, and Sebastian Misera. So first, I want to start off with this general message that unless maybe you thought about it or you worked in the area, maybe you're surprised that it's actually quite hard to compute string amplitudes. You usually get told in your string theory course that it's beautiful, and then everyone writes down the Virasoro-Shapiro amplitude or the Veneziano amplitude and tells you how beautiful it is. But then if you look at higher loops or more general settings, it very quickly becomes much harder than field theory amplitudes, let's say. But let's nevertheless start at this very nice Virasoro-Shapiro amplitude that we all love. So this is describing the 2-to-2 scattering amplitudes of gravitons. And I'll just talk about type 2 strings in this talk. It doesn't really matter whether it's type 2A or type 2B. And at tree level, you get this nice amplitude. So there's this tensor factor in front that has all the polarizations of the 4 gravitons in it. It's some tensorial structure that doesn't really matter for the rest of the talk because it's fully fixed by supersymmetry. So this will be the same at every loop order. And the really interesting thing is the function that is sitting here. So it's some function of the 2 Mandelstam variables, S and T. And we know that at tree level it takes this very beautiful form in terms of gamma functions. And so let me just point out some of the nice features. So it's manifestly crossing symmetric. So you see it's symmetric in S, T, and U. And it has this feature of dual resonance, where by putting in one series of poles in one channel, you automatically get the other series of poles. It is Regge bounded. It is UV soft in a sense that we'll also discuss later. Basically, if you increase the energy, but you keep the angle, the scattering angle fixed, the amplitude goes down exponentially fast. And of course, it's also consistent with unitarity. Okay, and it's analytic and all the nice things. And basically, I'm sure you're all aware, but basically this formula was guessed before string theory was around. So this is how the subject started. So today I want to basically learn similar things about the one-loop amplitude. And for that, I'll show you one general method that you can use to evaluate one-loop string amplitudes. But it's really maybe more appropriately titled How to Compute Integrals over the moduli space of the torus. Because you can also use that for other integrals that you might encounter. And to show you a little bit of what kind of results you will get is that if you try to compute now the type 2 one-loop amplitude, so this is flat space, 10 dimensions, no compactification, and at some fixed scattering angle, here I randomly chose 60-degree scattering angle, and then we can evaluate this amplitude. It doesn't have a very nice closed form formula as on the previous slide, but we still can evaluate it numerically. And you get a curve like this. So what are you looking at? You're looking at the energy on the x-axis. I put alpha prime to 4, just so that all the mass levels, so all the mass squares in this normalization are all the integers. And because of that, I'm also multiplying by the sine pi s squared, the amplitude, because otherwise I will get poles, or actually double poles at one loop on all the integers, and it will be an ugly plot. So I'll just multiply by this factor sine pi s squared, so I get nice plots, and nothing too special happens on the integers. And what I'm also doing is I'm taking an absolute value squared, and I'm plotting the imaginary part and the real part separately. And we're computing those in a quite different way. So the imaginary part will be much simpler. And it's notice that it's a logarithmic scale. So as I increase the energy, the amplitude drops down exponentially, just like the tree level amplitude does. And the yellow curve that looks a little bit more messy is the real part, and it has the same feature that it drops down exponentially. There's also this dashed line here, which is a certain prediction by Gross and Mende that we'll come to later, and that predicts this exponential fall-off. Should also mention that down here, you're basically talking about effective field theory. So as soon as you're sitting comfortably below the first massive mass level of string theory, you're basically having supergravity with various alpha prime corrections. And there is a huge amount of literature where people compute this alpha prime corrections, and so there's an alpha prime expansion, I think, to 7th order of the amplitude in the literature that you can find. And if you just plot that prediction, it's the blue and the yellow curve. You see that our way of computing kind of becomes much worse here. So we're kind of connecting with this, but we're actually not very good in going all the way to low energy for reasons that I'll explain later. Okay, so this is more or less what we'll be able to say. And now I want to tell you how to get to this kind of results. And I'll start by telling you how string amplitudes are defined. So there are certain integrals over moduli space, but with certain caveats that I want to tell you about. And then I'll tell you about the main way we evaluate these kind of integrals, which is via a procedure that comes from analytic number theory, developed in the 1940s by Rademacher, Hardy-Littlewood, and other people. And lastly, I want to talk about this high energy limit where there's this Gross-Mende behavior. So let's get started. If you read the textbook on string theory, then they will tell you something like this, that the amplitude at genus G with n points, so will be some function of the momenta, and it's computed by computing a certain correlation function in the conformal field theory and integrating it over the moduli space of Riemann surfaces. So there are certain, so this is, it depends of course a little bit if you're talking about tachyons or gravitons or superstrings or what kind of string theory, but roughly the structure is this kind of integrals. One thing that I want to point out is that when you write these kind of integrals, they're usually never convergent. So they're kind of formula integrals. And the reason is a very physical one, because if you would integrate such a thing over a moduli space, let's say these are always finite and real quantities, you could never produce physical features in the amplitude, like poles and branch cuts, and the amplitudes has certain imaginary parts, and so forth. And they come because these integrals are not literally convergent. And they come basically because there's these boundaries of moduli space, and all the IR singularities, which are these physical features in the amplitudes, they arise from regions in moduli space near the boundary. There are several resolutions to this that have been employed in the literature, how to make sense of these kind of integrals. And the one that I like and I want to use is the following, is one explanation why this happens is because usually when we discuss string theory, we treat the worldsheet as being fully Euclidean. So we very much like our 2D CFTs to be Euclidean because we can use complex analysis and so on. But at the end of the day, of course, it's not Euclidean. It's a worldsheet that starts its life as a Lorentzian worldsheet. And so really what we should be doing is to integrate over something like a Lorentzian moduli space of surfaces. And one way to implement this is to modify the integration contour. So instead of integrating over the moduli space of surfaces, you first complexify this moduli space, which sometimes is confusing because the moduli space itself may or may not be complex. So if you're thinking about closed string theory, it is already complex. So forget that it was complex. Now you complexify it again, and then you define some contour in this moduli space. And this contour basically on most of the moduli space, it looks the same. But if you go close to the boundary of moduli space, you modify the contour. How do you modify it? Well, the moduli, of course, if you're close to the boundary, you're talking about IR, you're talking about low energy. So you're close to field theory, and one of the moduli becomes the Schwinger parameter in field theory, so which is the proper length of the word lines. And you're just Wick rotating it to a Lorentzian proper length. And that means something on the level of the moduli, and it defines you this contour. So there's a certain way to define this contour, and you can think of it as a version of the I epsilon prescription, because of course in field theory you're having the I epsilon prescription, but you also need to implement that in string theory. And once you modify the contour in this way, all the integrals are absolutely convergent. So this is a convergent way of defining string amplitudes. Okay, and it was popularized by Witten around 2013. Okay, so what does it mean more concretely? Let's get to our one loop string amplitude. And the expression is well known. You can find it in Green-Schwarz. And it's an integral over the moduli space of tori. So the tori I labeled by a modular parameter tau. It's also an integral over the locations of the vertex operators on the torus. So there are 4 vertex operators. In principle, we need to integrate over all 4. But because the torus has a symmetry, we can use that translation symmetry of the torus to fix one vertex operator to one position that we like, and we only have to integrate over 3 of them. And then there's an integrand, and the integrand is given by pretty simple theta functions. These are just Jacobi theta functions. And it's modular invariant and so on, it's all nice. So it's a seemingly very straightforward integral. But it turns out that doing this integral is very, very hard. And basically all the methods that you know from field theory, they're pretty hard to apply in this case. One thing that I want to tell you is what this contour gamma means. So this is this modified contour. Usually people tell you, well, integrate over the fundamental domain of the torus. And the fundamental domain is basically is this keyhole region. So it's tau between -1/2, and the real part of tau between -1/2 and 1/2, and the absolute value of tau bigger than 1. And this is fine for everything down here because you're in the UV region. But once you go up there, the torus becomes very long and thin, and you're going to approximate field theory if you want. If you don't look very precisely, you might think you have a word line, and you need to wick rotate your Schwinger parameter. What that means concretely is that sort of the fundamental domain is kind of rotated because you're complexifying that space. So again, forget that tau was complex, complexify it again, you will get a 2-dimensional complex space. And you can say, well, one of the directions is real part of x and real part of y, where tau is x plus iy. But now this integration contour is folded in the region, in the imaginary part of y region. So you take the real part and the imaginary part of tau, and you complexify them again. And you get this kind of 3-dimensional contour. Okay, so, and once you integrate over this, everything will be convergent because basically everything here along this direction are phases, they're just oscillating, and then this 1 over im tau to the 5 makes it such that it's convergent in the end. Okay, so this is a well-defined integral, but because everything is oscillating now and so on, it's still very hard to put this on a computer and just integrate numerically. It's terrible. And also we are already seeing that the amplitude actually exponentially goes down, but if you look at the integrand, it goes exponentially up. So there's an exponential amount of cancellation, so putting it on a computer is terrible. Okay, so how do we evaluate it? So that's what I just said. It's convergent, but it's terrible for, say, numerical evaluation because the integrand is very highly oscillatory. So what we want to do is to do further contour manipulations because now we're in the realm of having a contour in some complex space, and the integrand is holomorphic in the sense that it's holomorphic in the complexification of the moduli space. It's a holomorphic function x and y, where x is the real part of tau and y is the imaginary part of tau. And so we can do contour deformations. So let's first do the easier part, and let's first compute the imaginary part of the amplitude. So the imaginary part of the amplitude fully comes from the region where the integral, the contour folds in this region, because the integrand is real, and so it's real for the usual moduli. So this part of the integral will only give real results. So if you want to compute the imaginary part of the amplitude, it's quite simple. You just have to take the difference of the 2 I epsilon prescriptions. So if you fold the contour in this direction, you used one sign of the I epsilon prescription. If you fold it in the other direction, so going into the slide, you have the other sign of the I epsilon prescription, and the difference gives you the imaginary part. And so the imaginary part is this contour that kind of only goes now through the slide. And the magic about this contour is that all the kind of complications that have to do with how the fundamental domain exactly looks like, they don't matter. And in fact, you can evaluate the integral over this contour by just knowing the local behavior of the integrand near infinity, because the height where you turn left or right doesn't matter. It's a contour deformation. So you can push the contour up all the way to infinity and just pick out, just know about the local behavior of the integrand there. So let me show you how that works in a simpler example. But it's the same idea, but just so you see what happens. And let's compute something that you also usually told you shouldn't compute, namely the one-loop amplitude in bosonic string theory, or one-loop partition function. So it's this expression where eta is the Dedekind eta function. And usually you get told it's not convergent. Yes, it's not convergent, but once you change the contour, it is convergent. And the one-loop partition function of bosonic strings perfectly makes sense, but it's not real, which also makes sense because it's unstable. So if you compute a determinant, one-loop determinant or something, there will be some negative modes, and the imaginary part of this partition function just tell you about the decay rate of the vacuum. Okay, so let's compute it. Let's compute the imaginary part. So it's given by this difference of the two contours. Let me call it gamma imaginary. And so now in this gamma imaginary, what we said is, well, is this contour that goes into the slide, and I can push it all the way up to infinity, so I can make my im tau as large as I want. What that means is that while this 1 over eta to the 24 has some expansion, sorry, the sign is wrong here, that's kind of important, this is supposed to be a plus. So this is the piece that is growing that usually you get told doesn't makes the integral divergent, and then there's like 24, and then there are subleading pieces. And now you see that all the subleading pieces, they will die out as you take im tau to infinity, because the subleading pieces actually have minuses in the exponential. And so you can just omit them. And that should make sense to you physically, because they will not contribute to the decay rate. The only thing that will contribute to the decay rate is the tachyon in the bosonic string. And so it's exact to just omit them and just have this integral where I call im tau y, and again, this is supposed to be a plus sign. And then the imaginary part contour is just this contour that goes from 1 minus I infinity to 1 plus I infinity in the imaginary part of tau. And the 1 is arbitrary, it could be 17. And it's some Hankel contour, whatever, you just evaluate it in some number. So it's easy to evaluate. Very good. So this is the idea, and you just apply it to the full amplitude, and you get some answer. It's exactly the same logic. And the structure is as follows. Well, you get the imaginary part will be given by a sum, a finite sum over masses. And these are all the masses. So this answer is basically given to you by the structure of unitarity cuts in a quantum field theory. If you compute the imaginary part of a quantum field theory amplitude, it's a sum of all possible unitarity cuts that you can perform on the amplitude. So which means that you can exchange some massive particle here and some massive particle down here, but the mass has to be such that you have enough energy in the amplitude to actually produce it. And so this is why this inequality is there, is some kinematical inequality. And the sum over masses is just the sum, this is in the derivation, this is the constraint that the corresponding term in the expansion of the integrand is actually divergent as you approach the cusp. So in technical terms, these are sometimes called polar terms. And then, well, you can do some of the integrals and some are left over. And after all the dust settles, you get one sort of Virasoro-Shapiro amplitude here, one Virasoro-Shapiro amplitude for this part, and you get some kinematical factors. So this is a Gram determinant because you have to integrate over the on-shell phase space. And then there's some polarization sum because this is massive exchanges. So there's a huge amount of sum over polarizations. And if you would do this in field theory, it becomes massively complicated very quickly because you have to construct all the massive string states and compute the polarization sums and so on. But if you just extract it from the one loop amplitude, it's kind of straightforward, and it gives you some polynomials, and they are represented in terms of some generating function and so on. And it's a squared because it's the square of the answer that appears in the open string. Okay, so this is the structure. And this, if you implement this on a computer, you can pretty quickly get this blue curve. So it's not trivial to implement, but it's also not very hard. And you need to do still 2 integrals. So you saw, if I could just go back, there's still 2 integrals because of this integral over the on-shell phase split, but these integrals are completely convergent. There's nothing bad in them. And you see in this representation, all the physical features have been made manifest because you get a sum, finite sum, and if you increase S, you can get new terms. These are the discontinuities and the branch cuts that are in the amplitude, and also the poles in S, they're manifest in these gamma functions. So all these singularities that you do expect, they're already there. Okay, and so that gives you this blue curve. But now what do you do for the real part? Because that's really the thing that you could say is the new thing that you cannot get just from the optical theorem, say. And you would expect this much more complicated. And there the idea is that you sort of recycle the computation for the imaginary part, but infinitely many times. So let me tell you what this means. Let me first tell you what happens for the open string, because it's easier to draw pictures. So for your open string, you have to similarly compute an integral, but it's only integral over tau holomorphically, but not d squared tau. So it's a one-dimensional integral. And roughly speaking, you have to compute a one-dimensional integral, turns out to go from 0 to 1/2, but that's not really important, over the modular parameter of some modular object. Okay, that's the integrand. And what you do is to do a sequence of contour deformations. And this was the sequence that was invented by Rademacher in the context of analytic number theory. So what you do is you draw all these funny circles. They're called Ford circles. Their radius is something like 1 over twice the denominator squared, and they touch the real axis at all these irreducible fractions. And they give this very nice pattern that they all touch, but never overlap. And the original contour is this one that goes from 0 to 1/2. And you see what you can do in the nth step of this deformation is that you take the contour that goes around the circles whose denominator is at most n. So meaning in the 5th step, let's say you go up to the circle C1/5, you go around the C1/5 until you hit the C1/4, you go around the C1/4 until you hit the C1/3, you go around that until you hit the C2/5, take the C2/5, and you go around C1/2 until you're there. That's clearly contour deformation from there to there. And then what you can do is you can cross your fingers and you can take n to infinity, and you hope that everything will converge. Because in the limit n to infinity, you get a contour that goes around all the circles exactly once. You can see here you're already going around the C1/2 almost entirely. If you make this denominator bigger and bigger and bigger, you will sort of, this contour will be more and more complicated. And in the limit, you get all the circles. And so this was applied, this technique, to the open string in these 2 papers. And why is this helpful? Because once you have integrals around circles, well, a circle around some fraction the real axis by modular transformation is the same as an integral over a horizontal line. Just apply a suitable modular transformation. For example, the integral over the circle near 0, if you take tau to -1 over tau, is the same as an integral over a horizontal line. And it's actually exactly the same computation as we just did for the imaginary part. This is exactly the same contour as before. So this means that once you do this, and provided it converges, you get something where every step of the computation looks very similar to the imaginary part. There will be some additional phases and stuff, but essentially that's what it is. Okay, so if you do this again for the toy example, because the real thing is kind of a complicated computation, so you want to compute the real part of this, then you hit the additional problematic thing is that this is now an integral over the fundamental region. This is not exactly what we discussed in the previous slide. But you would still hope that you can somehow compute this by knowing all the singularities of the integrand. So what you essentially need is a 2-dimensional version of this Rademacher expansion. I should say also that in the literature there are many ways to approach this that compute this integral. So here are some. Hopefully there are probably more. But if you do it in this Rademacher way, it turns out that you can do it, but it took us a while to figure out, and we needed the help of these people in Cornell. So there is a version, and this basically holds for any modular function. There's some boundedness condition that if you compute this integral over the fundamental region, well, really that's kind of Lorentzian version of the fundamental region, and you want to know the real part, because the imaginary part is easy, you can express this as an infinite sum over a contour integral, this is now in tau and tau tilde, of the same function. And this contour integral grows around the same Ford circles in, say, tau tilde, but over the horizontal line in tau. So there's a modular transformation, so this thing is modular invariant, and they're simultaneously transforming tau and tau tilde, where tau tilde, I'm calling tau tilde minus tau bar, so that tau tilde is also in the upper half plane. Yeah, the main point is that this is a sum over all these kind of Ford circles, and there's some additional factor that doesn't really matter, but technically it's there. And there's some kind of analytic number theory magic of some Dedekind sums and so on. You don't really have to worry about it. The main point is that you can write this integral as the sum, and all these integrals will be easy to evaluate, because again, you can push, like horizontal integrals, you can push them towards the cusp. And similarly, if you have these circles, you can make the circles as small as you want. You can shrink them as small as you want, and you only need to know about the singular pieces of the integrand near these circles. And the proof of this is follows from doing many contour manipulations and so on that you can read in the paper if you really want to. It's kind of fun. Okay, so just to convince you that this works, let me tell you the answer for the bosonic one-loop partition function. So if you want to compute this integral, you can do it. It will be an infinite sum representation, and so there's an absolutely convergent representation with some phases. So you see you get this e to the 2 pi I a over c, and you also get a star over c, where a star is the inverse of a modulo c. These are objects that very frequently appear in this Rademacher story, and you also get these Bessel functions, which are also very typical here. And you can very quickly, you can put this on a computer, it's very easy to implement, and it gives you very good approximations quickly, if you cut off the sum, say. And again, the imaginary part we already computed on previous slides, it was easy. And I just want to emphasize that this way of computing integrals over the fundamental domain, it's not really special to string amplitudes, it works for any modular invariant function, provided it satisfies a certain boundedness condition, and this boundedness condition translates to the fact that the sum has to converge absolutely. Roughly speaking, that is analogous, if you're familiar with the usual Rademacher expansion, it's analogous to the fact that the modular weight of the object that you're integrating has to be negative. So, okay, so this is the technology that we want to employ now. So we want to apply this, but now where the integrand is the actual string amplitude. So it's a some modular invariant object. And if you do this, you get kind of a mess, but you get a mess that is still much easier than the thing that you started with. And if you apply it to the full string amplitude, well, you also have to worry about the other integrals. You might, I sneakily only talked about the tau integral, but of course there are also the integrals over the other vertex operators, but they're kind of slightly easier, but they also contribute and they will make the sum bigger. So there's a sum over these fractions that come from this Rademacher expansion, but there's also a sum over certain winding numbers that come from this Z integral. But the main point is that you will get some kind of pieces of the answer. Those pieces are similar to evaluate to the imaginary part. So they have this, this unitarity cut of way of writing them with additional phases. And once you sum everything up and it turns out to converge, you get the full amplitude. Okay, so when is this good? Well, so still admittedly it's still hard because you still have to compute a very big sum, and every piece in the sum is also not terribly easy. So first of all, you might worry whether it's convergent, and the answer turns out to be probably it is. We cannot prove it. It seems to be convergent, but not absolutely so. But it at least numerically converges pretty fast, and it's practical for a region where S is not too small and not too big. The reason why it shouldn't be too small is if you take the Mandelstam variables to 0, the convergence actually becomes worse and worse and worse. because and the reason is because while this representation makes most of the analytic features manifest, there's one feature it does not make manifest, namely the massless branch cut in the amplitude. So there's the kind of massless branch cut that you also have in supergravity, and that is manifested in this formula because the sum starts to diverge. And so that's much harder. That's why it's actually kind of ironically kind of hard to go to low energies. It's also kind of hard to go to very high energies because there's a sum of polarizations involved in all this, even the imaginary part, and the sum kind of becomes more and more wild if you go up in energy. And so numerically, we can push to pretty high orders. It depends a little bit. If we compute the full amplitude, it's roughly order 10. If we compute some pieces like mass shifts and so on, we can go higher, but that's roughly what we can do. Although one thing I should point out is that I've been mostly complaining about this kind of cancellation if you do the direct numerical integration, which happens at large S. For small s, it's not really a problem. You can just directly integrate the amplitude and you get pretty good results. And of course, there's alpha prime expansion. Okay, so this is mostly the methodology. Let's look at some of the results. And let me first start with this in the forward limit. So now you make the scattering angle 0, and you plot the amplitude as a function of the energy. This is a pretty different looking plot than what we had in the beginning, where we had a scattering angle of 60 degrees. And in particular, it's not a logarithmic plot. It's a linear plot. And I'm also not taking absolute values because linear. I'm multiplying by s just to make it slightly nicer. And what you see is that the amplitude is kind of oscillating, and it's kind of order 1. Right? It's not really growing or becoming smaller, so it's of order 1 over s. And this is what you expect, because this follows from redshift physics. So there's a prediction from Amati, Cefaloni, Veneziano. There's also direct integration from Sundborg, which gives you the asymptotics of this formula. And we know actually that the asymptotic is purely imaginary. So the blue curves eventually wins over the yellow curve, which is not completely obvious from the numerics. And the reason is because the arrow is of order 1 over log s. So you have to go to ridiculously high energies. And you see convergence to this asymptotic result is actually rather poor. So that's maybe slightly discouraging. But sorry, for some reason I went back. That's the reason. But if you look at fixed angle scattering, it turns out that you actually much quicker go to asymptotics, which is this Gross-Mende asymptotics. So this is the same plot as in the beginning. Let me not tell you again the same things. But how does this Gross-Mende asymptotics work? It works, and I should be quick about this, by noticing that if you have an integral, so the integrand for two scattering in string theory is always of this form. So it's an integral over moduli space, some functions, and importantly, there's a function raised to the minus s and a function raised to the minus t. So that's always the structure. And you see that if you go to high energies, so you make s and t really large, then this integral will be dominated from a special region in moduli space, because you can do saddle point approximation on this integrand. And so this integral is approximately sum over saddles of this form, and there's some one loop determinant and so forth. So this is the argument of Gross-Mende, and they also tell you which saddle they think will be dominating at some genus G. And essentially they have some special saddle that they can construct. So at tree level it's easy, you just solve these saddle point equations. On the integrand, it tells you that the cross ratio is pinned to some specific value. At higher loops, it becomes much more complicated. And the saddle that they tell you that is always there is that you can construct a particular Riemann surface as a G+1 fold cover of the sphere that is branched over 4 points, and those 4 points are exactly the ones where you insert the vertex operators. Let me just tell you what this means from the space-time point of view, because I think it's kind of interesting. When we think about string scattering, we have some string going in, string going out, and then we usually draw some kind of holes in it for higher genus. But actually the saddle point at high energies, it is just the same as the tree-level scattering, but just the same worldsheet G+1 times on top of each other. Just take the worldsheet in target space, take G+1 copies, cut it open, and reconnect it in different ways. Formally, from the worldsheet, that looks like a higher genus surface. But from target space, it just looks like a worldsheet that does that. So it's kind of funny that it's kind of fake homogeneous, if you want. Okay, and there's a bunch of challenges and problems with Gross and Mende that let me not go too much into. But the only thing I want to mention is that because the integration contour goes over this complex modular space rather than the real one, in our way of thinking, there might be other saddles than the Gross-Mende saddles that are actually outside of the real modular space, but are on this complexified modular space. And also, it's pretty hard to compute their multiplicities. So what we did is just brute force. We computed the amplitude because we know how to evaluate it, and we compare. And if you compare the explicit data, and what I did here, you see now S goes much higher than it did previously, but I'm only computing the amplitude on integers, because on integers it's much easier to evaluate because it's computing the decay width. Because remember, at integers, the amplitude has double poles, and the residues of these double poles are the decay width of particles, and they're technically much simpler to evaluate. So we can push it much further. And if you just compute them, you get this curve. And this is, again, at some fixed angle, 90 degrees this time. Then normalized in some particular way. This is the scaling that Gross and Mende predict you. And if you include all the factors and so on, Gross and Mende actually would predict you this red curve. So it's not terrible, like given that this we're multiplying by some exponential factor and so on, but it's also not quite there. So one thing that you can, first of all, what I did is to include also the sub-leading correction from Gross-Mende. This is why this is not straight line, but it doesn't really matter. But one thing that you see is, first of all, the multiplicity of the Gross-Mende saddle should not be 1. Turns out it needs to be 3 to match with the actual data. So the Gross-Mende saddle appears 3 times in the contour. And the other thing that you notice is because there are these weird oscillations, they actually come from these other saddles that are not in the real part of modular space, but are in the complexified modular space. We understand what these saddles are. We don't understand how to compute their multiplicities. So all we can do at the moment is we have this data, and we can tune the multiplicities such that the data fits pretty perfectly on the saddle point evaluation. Notice again, this is true for large S, so the fact that this doesn't match here is not a problem. And so this is the imaginary part. We can also do it with the real part. So the real part, from Gross-Mende prediction, the real part asymptotically is actually 0, because the one loop, the saddle point approximation around the Gross-Mende saddle is purely imaginary. But it's actually not 0. It's of the same order of magnitude as the imaginary part, and it's again oscillating and comes from these Lorentzian types of saddle. Okay, I'm really out of time, so let me just very quickly give a summary. So these contour deformation tools are very useful for string amplitudes, and for other things, of course, also. So in particular, they're numerically useful if you want to actually plot the amplitude and get numbers out and so on. And they allow us to probe the physics of this amplitude much further. To evaluate the amplitude, the important feature was that this Rademacher way of computing it only needs the behavior of the integrand near the cusps. So we actually never had to input what the integrand at the generic point in modular space is. We can get the answer from just knowing what happens near the boundaries of modular space. And also these representations make a lot of analytic structure manifest, and in particular they also make contact with this Gross and Mende limit, and the development that is still in progress is to how to figure out exactly what the multiplicities of these Gross-Mende saddles have to be in order to actually match with the amplitude. So thank you very much.
Yeah, thank you. Questions, Elias?
I have 2 questions. What controls the convergence of the Rademacher expansion sum that you had of the functions? And also, can you calculate the asymptotic form of the decay widths for high energy string states?
Thank you. So first question, let me get some backup slides. Okay, so this is the rough form of the answer. And the devil sits in these phases. And the phases basically are controlled by, they're more oscillating the higher the energy goes. So all these phases are exponential of s times something. And so if you make s bigger and bigger, there are more oscillations and tend to be more cancellations. That's why converges faster, at least numerically. Whereas if you let s go to 0, then all these phases go to 1 and convergence breaks down. That was the first question. Second question was if I can get asymptotic formulas for decay width. Not from these formulas, unfortunately, because what turns out to be very hard to control are these sum over these intermediate masses and these polarization sums and so on. So at the moment, we're evaluating this numerically and comparing to Gross and Mende, which we can compute analytically up to the saddle multiplicities. So, and those we are fitting.
All right. Yeah, I also have two questions. The first one is, when you compare the Gross and Mende, you looked at integers. That seems very particular. Did you also check other values? Because maybe you said that already.
No, I did not. So thanks. So we did check with other values, but it's just a numerical problem at this point. It's much harder to compute the amplitude at generic values than at these integers. It does match. There are also they're also on top of what I mentioned. These multiplicities can be like trigonometric functions, basically, because there are saddles where if you say take z1 around z2, but you're not doing that with z2 bar around z1 bar, you get additional phases and they can resum in trigonometric function. This actually happens at tree level. And so also those trigonometric functions you have to guess, but we make some guess that works. So
I could imagine that the factor of 3 was just due to picking particular points, but you sort of checked that.
Yeah, we check at other points as well. And actually, if you look at the amplitude, it's very important to check these other points because the amplitude tends to oscillate roughly. I mean, there's this kind of oscillation, but then there's also faster oscillations that you can see in the plots that are roughly period 1. So it actually goes up and down period 1, and they come from this other trigonometric function.
Second one was these sums, the Rademacher sums. Do you have any intuition for what they mean?
No, it's a kind of a magic. In particular, you see it fails exactly for field theory. That's kind of the, if you want, annoying or exciting, depends on your perspective thing, that they only work for string theory amplitude. They do not work for field theory amplitude. So it's kind of a stringy magic. And in particular, if you show this to field theorists, they're kind of, it's very peculiar that you have like unitarity cut representations or almost unitarity cuts with additional phases for the real part of a one loop amplitude. That's a thing that shouldn't work, but yeah. Thank you.